Hello everyone, in today's lesson we're going to be looking at lesson 8, function notation. In our previous lesson we looked at what a function is. A relation involving inputs and outputs is a function if every possible input only has one possible output. For example, we look at these ordered pairs that form a particular relation. We see that each input is unique. The inputs are not repeating. Even though the outputs are all the same, the inputs aren't repeating, so this is a function. Let's assume these three ordered pairs were actually connected to each other. What would that look like? We have our 2, 2. We have 3, 2, perhaps something like this. And we have 4, 2 right here. If these three lines were connected, we could ask ourselves the question, does it pass the vertical line test? We say that a function passes the vertical line test if I were to draw a vertical line anywhere along the graph and it always only touches one point on the graph. And if that's the case, then it passes the vertical line test and it is a function. If at any point on the graph it touches more than one point, then it fails the vertical line test and it's not a function. Again, you can think of functions as just this special type of relation that has to follow this particular rule. Let's look at today then at what a function notation is. Notation signifies that this is just one particular way of writing or expressing something. We actually have multiple notations where we can use functions. So for example, we can use mapping notation. This is simply saying f being function. Here's my function, introducing it with a colon. X is such that 2x plus 3. So that's saying if I were to insert this unknown value of x into my equation here, I would have 2x plus 3. I could say function, here's a function using mapping diagram, where I'm saying I'm going to insert 5 where x was in our original equation. So you can see here we are replacing the x with 5. And that's saying that if the value of this function was actually 5, or if the input value here is 5, then the output has to be 13. We follow the same concept we did before with our mapping diagrams, where we have our input on the left-hand side and our output on the right-hand side. Now, most commonly when talking about functions, we're actually not going to be using the mapping notation, but rather a function notation. You can see here that we are replacing what we normally would have written as y equals, and we're changing that with into f of x. So we're saying, look, we have a function here where the input is x, and this is what the mechanisms for getting that output is. This is what we are going to do with that input of x. Now, as an equation, we simply wrote y as the output. Output is equal to 2x plus 3. But again, in function notation, we're saying this function with the input of x is equal to 2x plus 3. So again, just a different way of writing it. But I want to be very specific about how we say this f bracket x. The way we say this out loud is f of x. But here the of does not mean multiplication. I know we always say in math that the word of means multiplication, but this would be your biggest exception here, okay? We're simply saying function of x, or other words, f of x is equal to 2x plus 3. So let's say we're given this particular function here, and then in the next step we're told that the input is actually 5. What we can do here is simply replace x with 5. If we replace x with 5 here where it says f of x, then we also do so in our actual equation, and that's how we finally find what the outcome is, what the output is when the input is 5. So we can say that in f of x, or in function of x, the output is 13 when the input is 5. The use of the letter f here is simply the name of this function, okay? F is the most common, but it doesn't always have to be f of x. I could have another function that's called g of x. I could have d, oh, actually d is not very common, but I could have d of x. I could have even h of, let's say if my variable was actually g instead of x, that's completely fine. What's going on here is that g, d, and h, these are names that we are giving to these functions, or names we're giving to these equations. And the name symbolizes that it is a unique function in a particular scenario or a particular problem. On page 466, we'll see some examples here. We have two functions we're given. The first function is named f, and we have f of x is equal to 2x plus 5. The second function has a name called g, and it is g of x is equal to 4 minus x. So now let's look at the question. F of 3, what would f of 3 be if given that f of x is equal to this particular equation? So we can simply start by rewriting the original equation that was shown, but instead of where x is, we can now replace that with the input given in the question, which is 3. That gives us 9 plus 5, which is 14. So we know that when f of x is equal to 3, we have an output of 14. In the second question here, we're no longer looking at f. We're looking at another function named g. So we look at g. G is defined by 4 minus x. And we see here that instead of x, we now have an input of 1. So we're going to replace what was originally x in our equation with the value 1. So we know that g of 1 is equal to 3. Now go ahead and try out C and D on your own. You can pause the video, and the answer will show here in 3, 2, and 1. There you go. Did you get the answers? If you have questions about these simple substitutions, please feel free to send me a message and let me know. Let's look at E here, a slightly more complex question, but the theories are the same. First, we're looking at f of 0. So we're going to take our equation, x squared plus 5. But instead of x, we're going to replace that with 0. I'm going to put a big bracket around it to remind myself that this is all a part of f of x function minus g of x. Okay, I'm going to draw another big square bracket, but here for g, I have 4 minus, instead of x, I have 0, and a big square bracket again. Now, this is a very simple function because they're giving us the value 0 in here, but I'm using the square brackets because it is the best thing to use to keep our two functions completely separate and make sure we honor the symbol in the middle that is connecting them. 0 squared is just 0, so my function, my f of 0 is going to equal 5, and my g of 0 is going to equal 4. There you go. That tells me when the input of when the input equals to 0 in f of x, the output is 5. When the input is equal to 0 in g of x, the output is 4. Different outputs again because, well, they have different names. They're completely different functions, just two people or two functions who are one subtracting another. That gives us the output 1. In example 2 here, you'll see some different ways of it basically telling us what the value of x should be and how we can substitute the input for actually another variable. Go ahead and try out ABC on your own, and the answer is going to show up here in 3, 2, and 1. All right, now let's try some substitutions where we're actually using an expression or a different variable. I'm going to go ahead and jump to f for our example. I have f of 2x here, which means every time I see the value x in my original equation, I'm now going to replace it with 2x. So here I'm just going to write it out first. Okay, we're going to replace every original x with a bracket 2x. And the bracket is extremely important because we have other things that are affecting the value of x here. For example, our exponent. If you don't write the bracket, totally different question. Because we're going to have to start with dealing with the exponent. I have 5 times 2 to the power of 3 and x to the power of 3 minus 2 times 2 is 4x. And then I simplify it, checking to make sure that they are different terms, so I actually cannot combine them, and there we go. And here's the answer for E as well. You can pause the video to copy that down. Let's move to example number 5 on page 467. Specifically, I want to look at number 2 here. It gives us a function f of x is equal to 2x minus 5, where x belongs to real numbers. Okay, so we know that it could be any value. There are no real domain restrictions here for x. It says here to solve for the equation f of x is equal to 4. that means I actually need to find out what the value of x is. I have an output, now I'm going to find the input. So let's write out our equation. Output of 4 is equal to x squared minus 5. Using our inverse operations, we have 4 plus 5 on this side, and x squared minus 5 plus 5 on the other side as well. 9 is equal to x squared. That means x is equal to square root of 9. But be careful here. Whenever we take the square root of a number, we always assume it could be both positive or negative. So that means x is equal to either negative 3 or positive 3, or actually in this case, since it's all real numbers, it is both. And there you go. That's your final answer. I'm going to take a moment to break down what that actually means for us, though. If we had ordered pairs for this particular equation, we would be saying that we just found two possible pairs. When x is equal to negative 3, y is equal to 4. And when x is equal to positive 3, y is also equal to 4. Sorry, I think I said negative, positive 4. So it's still a function because the input value is not being repeated, only the output. Let's look at one more example here in question 5C. It says to solve for the equation, again, we are given an output value. We're working with the same function here, okay? Which means we could actually end up, we should end up with a positive and negative again. But this time, it gives us a particular parameter for the domain. Remember, domain means a range of numbers that the input value is allowed to be. It's telling us here now that the input value has to be greater than 0. So we no longer have to deal with the negative side. The second thing I want you to note is that it is asking for an answer in simplest radical form. We're going to look at what that looks like in just a second. First, I take my original f of x. I am now giving it an input of t. F of t is equal to t squared minus 5. F of t is equal to 75, so I replace this particular value here, f of t, with the output 75. And we're going to solve for the value of t, and that gives us square root of 80. So, jogging your memory back all the way to Unit 1 in grade 10, we're looking at simplifying radical form. So I'm looking at the square root of 80 and asking myself, is there anything I can factor out of the number 80 that is actually a perfect square? Well, 80 is a combination of 16 times 5. So that means t is equal to square root of 16 times square root of 5. Square root of 16 would give me 4. 4 times 4 is 16. So I have 4 and square root of 5. There we go. This will be your final answer in the simplest radical form. You'll be using the simplification in homework questions number 11 and number 14 for today, but you can find the full list of homework questions in your OneNote or PowerSchool.